Good evening, everyone. Good evening, everyone. Am I audible?
Yes, you are audible.
Okay, thank you. So, today we will start with neutralization titrations. In the previous class, we had just learned about some of the basics of neutralization titrations, like those including strong acid and a strong base, a weak acid and a weak base, and so on. So, today we will learn about neutralization titrations, the role of solvent. We will also talk about non-aqueous titrations, why dielectric constant is important for such titrations. We will also learn about Hammett's acidity function and other applications of such titration. So the before going for titration reactions, we will just first understand why non-aqueous titration is essential for us. So
Madam, presentation is not visible.
So I'm sorry for the disconnection here. So we were talking about the use of non-aqueous solvents in titration reactions. So when we particularly use a weak acid and weak bases in such type of titrations, the determination of equivalence point or endpoint is very difficult. So these processes, they can be overcome by the use of non-aqueous solvents, because we know that many organic acids, they will be soluble in methanol or ethanol. So that is why sometimes non-aqueous solvent is mostly preferred for many titrations. So then there are also many problems, like in normal titrations of weak acid in aqueous medium. So one of the problem is the acid and bases which have the ionization constants less than about 10 to the power minus 7 or 10 to the power minus 8 range. So they are very much weak, and the titration in conventional methods, that is in water, it is very difficult. So what we do in such cases, we choose a solvent which is less basic in water. So as a result, what happens is that since the solvent is less basic in water, we can titrate weaker bases, the bases which are weaker. So here the same principle is also applied for titrating a weak acid. So what happens is, if we choose a solvent which is less acidic in water, then we can titrate a very weak acid, and thus with the use of proper, like with the proper choice of a solvent, we can titrate a very weak base and a very weak acid. So like whenever we do an experiment concerning a very strong acid, that is 0.1 and HCl, versus a strong base, that is, let us say, zero point 0.1 normal NaOH, then we can see that the jump in the pH at the equivalence point is by almost 5 to 6 units, because it is a strong acid and it is a strong base. So what happens here is the calculation of equivalence point is very much easier in the case of HCl versus NaOH. But the problem arises if we take a weak acid, that is acetic acid, and the jump in the pH, it only increases by hardly 2 points. So what happens is here is the calculation of the equivalence point becomes difficult. So here, as you can see in this figure 9.1, here it shows the titration curve of a weak acid with a weak base. Here it is shown. Now, even if you look at this for acids having pK 3, 4, 5, 6, 7, still it is somewhat easier for us to calculate the equivalence point. But as the pK increase above 7, the calculation of the equivalence point beyond this point, it becomes difficult. So for acids with pKa greater than 7, the difficulty arises. So what happens here is, for such type of acids, we generally employ non-aqueous solvents. So now here what we see is, this is just an example. So when we use a non-aqueous solvent, which is mostly strongly, it is acidic or basic in nature, so here we can see that the problem arises where the pK or pKb of the material concerned is greater than 7. Now the end prayer point break, here it is shown as I have shown in this figure 9.1. It is very difficult to calculate. So for example, let us consider the reaction in equation 9.1, that is A minus plus H2O forming Ha plus OH minus. When the pKa of this Ha here, then the basicity of A minus is considerably high. So what happens? It can readily accept a proton and it can form Ha. So the neutralization here is not 90%, even it is less than 99%. But the that is, even if it is 99.9%, then we can know the value. But with the increase in the dilution of the acid or alkali, when the inflection still becomes smaller. So as the inflection becomes smaller, which is even less than 2 pH, so what happens? The calculation here, it becomes very difficult. Now we know that in most of the acid base titration, phenolphthalein has been used as an indicator. So also it is a suitable indicator in the titration of a weak acid and a strong base. So this is phenolphthalein, we know, which has mostly been used in many types of acid base titration. So what happens is, when we add a small amount of weak acid, we have to use a dilute solution of NaOH for the titration. So it has been observed that for 0.01 normal or more dilute solution of NaOH, the pink color of phenolphthalein, it fades away rapidly at the end point. So what happens here is, because it fades away rapidly, there is difficulty in identifying the endpoint. So here, when the pink color appears, then as it disappears, now it is necessary to shake the solution. So there is a thorough mixing. So in order to confirm this, whether the endpoint has arrived or not, a drop or two of the titrant are then added when the whole solution appears to be faint pink. But when we shake it very vigorously, it fades away rapidly. So this is what we call it as the fleeting endpoint. So due to this problem, because the endpoint arrives rapidly and it goes away, we call it as a fleeting endpoint. And knowingly and unwillingly, we add a few more drops of the titrant from the burette to locate the endpoint then that is actually needed. So this is the one problem while we're working with a weak acid or a weak base. Now another problem in such type of titration of a dilute solution of a weak acid is the interference due to atmospheric carbon dioxide. So what happens is, here the carbon dioxide that is present in the environment, it interferes in the titration when we consider a weak acid. Hence, that what happens is, we perform the titration at a higher temperature to remove out the dissolved carbon dioxide. But the question is whether all the carbon dioxide has been lost or not, that we don't know. So here also there is a possibility, since we are using a weak acid, then a part of the acid will also be lost due to the heating. So these are the difficulties that are encountered in the titration of a dilute solution of a weak acid with alkali. We can say two types of problems, three problems that might arise. That is, first, the inflection on the pH neutralization curve is very small. Phenolphthalein color, it fades away rapidly at the end point, so detection becomes a difficulty. And the third is the interference due to the environmental carbon dioxide that interferes in the titration process. So to overcome all the three difficulties that we encounter during the titration of a weak acid or a weak base, if we by some means the dissociation constant of the acid can be increased so that it behaves like a strong acid. So this can be one way by which we can overcome these difficulties, and this process or this can be achieved by using a suitable non-aqueous solvent in place of water. So the three shortcomings associated with the titration of a weak acid or a weak base is mostly overcome by the use of a suitable non-aqueous solvent. So in order to understand what is this, we must first study the concept of acids or bases that we had studied last time, that is the Bronsted concept of acids and bases. So here we will first understand what does Bronsted concept say, and then we will apply the concept to the titration of a weak acid weak base in non-aqueous medium. So first we'll understand the acid base concept of Bronsted and Lowry. So here we knew that the Arrhenius theory, it explained the nature of a acid and base in aqueous medium, but however we knew it has some certain limitations, and one of its limitations is also that it failed to explain the acid base neutralization reactions in non-aqueous medium. So after the failure of Arrhenius theory, Bronsted and Lowry, they came up with a new concept, and according to this theory, an acid was defined as a substance which donates a proton, whereas a base is a substance which accepts a proton. So this is the basic idea of an acid and base that was provided by the theory of Bronsted and Lowry. So this concept was further extended to many substances which could not be identified as acids and bases by Arrhenius theory. So like for example, in the reaction that is given here in equation 9.2, so here we can see that ammonium NH4 plus H2O, it gives rise to NH3 plus hydronium ion, that is H3O plus. So if we look into this reaction in equation 9.2, we can see that ammonia donates a water to what sorry donates a proton to water molecule to become NH3. So since ammonium donates a proton, it is an acid, and since water accepts the proton from ammonium, it becomes a base. So here the concept of acid and base by Bronsted and Lowry explains the acidic and basic nature of ammonium and water. Now, in the Bronsted model, any substance in any medium is a base if it can accept a proton. So, what does this line mean? Here we will consider two equations, that is equation 9.3 and equation 9.4. When we look into equation 9.3, here ammonium, it donates here, it accepts a proton to become ammonium ion. So, here ammonia is a base. Here in both the cases, if we look into both these cases, ammonia accepts a proton, that is NH3 plus H plus, forming NH4 plus. So here it can accept a proton, although it doesn't contain any hydroxyl group. So the Bronsted theory here, it was shown that the Bronsted-Lowry theory, it can now be applied to non-aqueous solvents. So some of the acid-base reactions in different solvents as per Bronsted-Lowry concept are illustrated here in table 9.1. So here in the first equation, the solvent is ammonia, acid 1 is acetic acid, base 2 is ammonia, and acid 2 is ammonium The base one here is acetate ion. So this is how in non-aqueous solvent acid base has been identified. The basic solvent here, in this case, it facilitates the loss of proton from a very weak acid. So as a result, the weak acid, it becomes much stronger in effect. So this can be similarly extended to cases where the solute is very acidic, very basic, and upon adding an acidic solvent, the solute effectively becomes a stronger base. So here table 9.1, also in table 9.2, here are the data for various non-aqueous titration medium. Here in table 9.2, if there has been the acidic solvent reagents have been shown here. Now the most commonly used procedure is the titration of organic bases with perchloric acid in anhydrous acetic acid. This is the most commonly used media for non-aqueous titration. Now, glacial acetic acid is an amphiprotic solvent and it is widely used for the titration of weak bases like amines, and it ionizes as follows, like RNH2 plus acetic acid forming RNH3 plus acetate ion. The acetate is then titrated as hydroxyl ion in water. So here the use of perchloric acid is that it is the one of the strongest mineral acid, so it is usually used as the titrant. It is dissolved in acetic acid and it is used as the titrant. Even if this acid is only partially dissociated in glacial acetic acid, but the same extent as acetic acid in water. So that is why perchloric acid is mostly used in non-aqueous titrous reactions. A compound, when dissolved in the suitable non-aqueous solvent, it is then titrated with the standard solution of the acid or base, which is then dissolved in non-aqueous solvent. But how can we know the end point in such cases? Well, we can visually, like in normal titrations, we can visually see the end point, or we can use a pH meter. The convention of acid or base number is used to overcome any ambiguity which can be used in the expression of the base content. So the Bronsted theory, it defines acid as any species having a tendency to lose a proton and can do so only when other substance is present to accept protons, which in turn the submaterial which accepts the proton, it acts as a base. Here an example has been shown in figure in equation 9.5. Then now coming to different types of solvent systems. So when we will talk about the non-aqueous solvent systems have been classified basically broadly into three groups. So one is the amphiprotic group, one is the aprotic group, and the third is the basic but not acidic, that is the non-ionizable group. So coming to the amphiprotic groups, amphiprotic solvents, they are those which possess both acidic and basic properties such as water, ethanol and methanol. Then they are ionizable in nature. The amphiprotic solvents, they undergo self ionization, or what we call it as autoprotolysis. Here it's shown in equation 9.6 how they autoprotolysis, where here H solvent, it represents the hydrogen containing solvent. The autoprotolysis constant here, it is given as, from the K is given as the concentration of the H2 solvent plus into the concentration of solvent. So these have both acidic and basic properties. So acetic acids and alcohol like methanol, ethanol, they are called as autoprotolytic solvents or amphiprotic solvents. They are dissociated to a slight extent. The dissociation of acetic acid, which is used as a solvent for titration of basic substances, we know is given in the form that is shown in 9.8. So here in the dissociation of acetic acid, the acetic acid, it functions as an acid. Now, whenever a very strong acid, that is perchloric acid, it is dissolved in acetic acid, here the latter can function as a base and combine with protons that is donated by the perchloric acid to form the protonated acetic acid, which we call it as the onium ion. Now, perchloric acid here in equation 9.9, you can see it's ClO4 giving rise to H plus ClO4 minus. Now, the acetic acid will combine with the proton of the perchloric acid. Here, CH3COH plus H plus, giving rise to the protonated acetic acid, that is CH3COH2 plus. So this is generally called as the onium ion. Now here this onium ion, it donates its proton to a base very easily. So a solution of perchloric acid in glacial acetic acid, it functions as a strongly acidic solution. Now let us talk of pyridine. Pyridine is a weak base. It has its basic property enhanced when it is dissolved in acetic acid. How is it possible? It is possible therefore to titrate a solution of weak base in acetic acid with perchloric acid and to obtain a sharp endpoint. So here some of the equations have been shown how pyridine acts as a base in per acetic acid, and upon adding with perchloric acid, the titration is unsuccessful. We can add with here adding HClO4 to this, we can then titrate the our required substance. Then coming to aprotic solvents. Aprotic means they are neither acidic nor basic. That is, they are called as inert solvents such as benzene, toluene, petroleum ether, carbon tetrachloride, etc. So such type of solvents, they are neutral. They are chemically inert substances. They are not much acidic or basic. They have low dielectric constant, and they are very much non-reactive. So as a result of their non-reactivity, they do not favor ionization. So if we add picric acid to benzene, we get a colorless solution. But when we add aniline to picric acid, the solution becomes yellow. So what does this indicate? It shows that picric acid is not dissociated in benzene, but the presence of the base aniline is a base. It functions as an acid, and due to the formation of the picrate ion, the yellow color it develops. So since dissociation is not a primary factor for neutralization, aprotic solvents are often added to ionizing solvents to depress or to suppress solvolysis. Solvolysis is similar to that what we call as hydrolysis, and of the neutralization product to sharpen the endpoint. Then there is one, this aprotic solvents are also, we have two specifications. One is protophilic solvents. These are basic in character and they react with acids to form solvated protons. Here, acid plus basic solvent to form solvated proton plus the conjugate base of the acid. So a weakly basic solvent, it has a very less tendency than a strongly basic one to accept a proton. So whenever a weak acid has a less tendency to donate protons than a strong acid, that we know. So what happens is, as a result, a strong acid such as perchloric acid, it has more strong acidic properties than a weak acid such as acetic acid when it is dissolved in a weakly basic solvent. So this, all these acids, the such type of effect, when they become different in their strength, they differ in their strength when they are put in different types of solvents, and such difference in strength is occurring because of their affinity to the bases or their affinity to the solvent. This is called as leveling effect. Strong bases are leveling solvent for acid. Weak bases, they are differentiating solvents for acids. So this is one important information to always remember. Then there is protogenic solvents. Protogenic solvents are acidic solvents like sulfuric acid. They exert a leveling effect on bases. Now coming to the third category of non-aqueous solvents, one is they are the basic but they are not acidic in nature. That is, they are non-ionizable in nature. The examples include ether, dioxane, ketone, pyridine. Now how can this react? So what happens? The nature of these, uh, they indicate that they are non-ionizable in nature. So how do they react with an acid? Well, what happens is the ethers have the basic oxygen through which they can react with an acid, and pyridine also do by through its basic nitrogen. So basic oxygen and basic nitrogen, it indicates the presence of the lone pair there. So it is seen that the bases do not react with just such type of solvents, they are just solvated. So there is, however, most of these are extremely weak bases. So there has been no known examples of solvents that are acidic but not basic. So then coming to the importance of dielectric constant. So we know that for any particular solvent, the dielectric constant, it measures the ease of separation of the two oppositely charged ions, or it is the ease of dissociation of an ion pair that is present in the solvent. So let us consider the acidic behavior of acetic acid in water and in ethanol. So we know it has been found that the dielectric constant of water at 25 degrees centigrade is 78.5, whereas it is 24.3 in ethanol. So now, when we dissolved acetic acid in both these two solvents, looking at the dielectric constant of these two solvents, we find out that the dissociation of acetic acid will be greater in water than in ethanol, because the dielectric constant of water is much more higher than that of with ethanol. So whenever we have to select a particular solvent for titration purposes, we also need to consider its dielectric constant. So this is also one crucial factor that we also need to always remember, the dielectric constant of the solvent. Now coming to Hammett's acidity functions. So commonly used acidity functions, whenever we use acidity functions, we indicate that whether they are concentrated acid or basic functions. So acidity functions, they are established over a range of composition of a such system by UV visible or NMR measurements by the degree of the hydronation, that is either protonation or by the formation of Lewis adduct for the members of a series of structurally similar indicators or bases of different types. The best known is the Hammett acidity function that we call as H0 for the bases that are uncharged. It is a measure of acidity that is used for very concentrated solution of strong acids, even the superacid. So it is Hammett function is particularly useful for physical organic chemistry, where we come across various acid catalyzed reactions. So this Hammett acidity function is given as H0 is equal to minus log of activity of hydronium ion into gamma B by gamma H plus. So here gamma A represents activity and gamma represents the activity coefficient of a base B and its conjugate base BH plus. So here in table 9.3, some of the Hammett function for some of acids, here it is given fluoroantimonic acid, magic acid, carborane superacid and fluorosulfuric acid. The H0 here, the Hammett acidity function has been listed here. Then coming to titrants and endpoint detection. So we know here in non-aqueous solvents, perchloric acid has found greater significance. The titrations in presence of acetic acid or non-basic solvents, they are mostly carried out using perchloric acid as a titrant. So it is a very strong mineral acid and it is quite easily available. So many other acids are also available. Then what is the advantage of or merit using perchloric acid? The reason is primarily because that in acetic acid, the perchloric acid, it gives a longer potentiometric break than HCl. It also gives a longer break than nitric acid. So we have to choose a solvent in which the perchloric acid will be dissolved depending on the type of titration. So usually perchloric acid has been chosen in conjugation with acetic acid. The titrant here, it is prepared by dissolving required amount of 70 to 72% of perchloric acid, that is HCO4, HClO4 in acetic acid. Now we should always remember to use acetic anhydride to remove water from the perchloric acid. Mostly perchloric acid is associated with two water of crystallization here as it is shown here. To remove this water of crystallization from HClO4, we have to use acetic anhydride. This is a precaution that we have to follow whenever we are using it for titration of a very weak base. So now when we are after this solution is prepared, so what happen is we can add it the for the basic titrants in aqueous solution, the primary standard acid KHP here, that is potassium acid phthalate is used. So in glacial acetic acid, KHP is used as a primary base or stand for standardizing the perchloric acid. Then we have to apply heat to dissolve the KHP in acetic acid. So whenever we have to titrate weak acids in non-aqueous solvent, then we can use solutions of different sodium or potassium alkolates in a suitable solvent. In this category, we can obtain the best titrants from a solution of sodium or potassium methoxide in methanol or benzene methanol. Here in this case, methanol is mostly preferred as a non-aqueous solvent because it has a certain amount of acidity that is much more comparable to water. So such titrants, they are not in much use presently because and methanol is also toxic in nature. So that is why here this such type of titrations, they are not much used. Then coming to titration of quaternary ammonium hydroxides. As a titration for acids, tetrabutyl ammonium in 2-propanol is often used. The advantage of using is that tetraalkyl ammonium salt, it is the titrated acid in the, it is soluble in usual solvents. If we use the alkalis, then we will see that the alkali metal of titrated acids, they form precipitates. So also the potentiometric curves, they are very good with ordinary, they can be like easily detected with ordinary glass or calomel electrodes. Now, basic titrants, they can be standardized by the primary standard benzoic acid. So here, for acidic titrants, we can use KHP, and for basic titrants, we can use the standard benzoic acid. Now, coming to the titration of halogen acid salts or bases. The halide ions, that is the chloride, bromide, and iodide, they are quite weakly basic in nature. So they cannot react quantitatively with the acetous perchloric acid. Acetous perchloric acid means the perchloric acid which is dissolved in acetic acid. So here in this case, if we add mercury acetate, which is undissociated in acetic acid solution, to the halide salt, then the halide ion will be replaced by an equivalent quantity of acetate ion, and it is which is the strong base in acetic acid. Here it has been shown here in represented in 9.8 to 9.20. So here what happens, then the endpoint detection for the titration will be done. The relative basicities of organic amines when they are titrated as bases in non-aqueous solution is the same here as in water. So here in figure 9.2, you can see the titration of amines in acetic acid with 0.1 molar perchloric acid, that is measured with glass calomel. Here it is glass calomel electrode. Different types of amines and their titration curves, and it has been here A, B, C, D. A represent aniline, B represent para-bromoaniline, C for orthochloroaniline, and D represents para-nitroaniline, here quinoxaline. So the titration of amine halide salts, they need some modification because they are very weakly basic in nature. So their titrations cannot be carried out in dilute acetic directly in acetic acid. So if you add mercury acetate to the amine halide, it will convert the halide to undissociated mercuryc halide, and then we can carry out such titrations. The advantages of using mercury acetate is that it remains undissociated in acetic acid. So once it remains undissociated, so the calculation or the estimation becomes easier for the other ion. If the titrant, let us say it is very much diluted, then we can also mix some dioxane to increase the sharpness of the potentiometric endpoint. That is why in most of the cases, perchloric acid in in dioxane has been used when amine halides are used. So here in figure 9.3, we can see potentiometric titration curve. Two mixtures are taken. One is butylamine, one is pyridine, and they are titrated in acetonitrile with perchloric acid in dioxane. So the amines in this mixture, they can often be titrated separately whenever they have large differences in their basicity. So this is because, so if you see the titration of a mixture of butylamine and pyridine, here as shown in figure 9.3, we see that there are two potentiometric breaks. Here is one potentiometric break and here is another potentiometric break. So well, what happens is the using aniline, we can see that the endpoint corresponds to the sum of the amines. This because butylamine reacts with acetic acid to form the acetate ion, which has almost the same basicity of that of the pyridine. Now coming to titration of acids, sulfonic acids, carboxylic acids, phenols, enols, and other nitro compounds that contain different sulfur containing compounds, they are acidic to some extent. Now, this acidity, it enables them to be titrated in non-aqueous solvents, but certain conditions need to be maintained. One thing that always needs to be maintained is that the solvent should not have any properties, acidic properties by itself. So it will be able to dissolve the other acidic compounds. Also, in the mixed such cases of mixture of acids, the solvents should not be a strong base so that the mixture can be titrated appropriately. So a strong base like sodium ethoxide or tertiary butyl hydroxyl hydroxide, it will dissolve in benzene methyl alcohol, isopropyl alcohol. It is mostly used as a titrant in for titration of acids. Now, coming to some applications of such non-aqueous neutralization titrations, here the pH conditions we need to be maintained for various types of manufacturing industries. So, but starting uh, from food industries to pharmaceuticals to cosmetics, so maintaining maintenance of pH is very important. So we have to always check whether the acids and bases in the reactants as well as the products, so what is the influence, whether they have reacted properly, and what is the nature of the final product that we are obtaining. Acid based titrations, they are also used in analytical method. This sort of they can be used in Zeldal method for determination of nitrogen. Pharmaceutical industry, we know in pharmaceutical industry, in agriculture, we need to find out the amount of nitrogen that is present in soil. Also in pharmaceutical company, we need to know the amount of nitrogen that is present in a particular drug that is synthesized. So these cases, so particularly in such cases, direct titration of amine salts becomes very important. Then the endpoint of these titration, mostly it is done through eyes only, that is by visual observation. But when we are dealing with very dilute or colored solutions, then visualization becomes very difficult. So in such cases, we can get accurate results by the use of the potentiometric method for identifying the endpoint. So here we need an electrical apparatus, that is either it can be a potentiometer or a pH meter, which can identify the endpoint of the titration. So the refer here for a particular, when we for this we need a indicator and a reference electrode. Also we need a burette, a beaker, and a stirrer. The reference electrode, it should have a constant potential throughout the titration. So according to a particular titration, we have to choose the indicator electrode depending on our need. So when we take a, let us take a glass electrode for acid base reactions and a platinum electrode for redox reactions. So the choice of electrode lies as per our need. Also the equilibrium should be reached rapidly. We have to immerse the electrodes in the solution to be titrated, and then first we measure the potential difference across the electrodes. Then we add measured volumes of the titrant with continuous stirring. The stirring must be done. Then we measure the value of the EMF or the pH. Then we have to note that the burette reading corresponding to the maximum change in the EMF or the pH value per unit of volume. This we can do graphically. Then after adding, we will keep on adding small volume of the titrants. When the endpoint is reached, then we can stop our titration. However, when the endpoint is very small, then we will slow down the process and add the titrant very minutely to, and from the graph we will calculate the slope of the curve. So now when we plot this graph of the change in EMF or the change in pH against the volume of the titrant that has been consumed, we will get a differential curve in which the peak is the equivalence point, and then we can identify the endpoint of the titration. So this is how the neutralization titrations, they are important in analytical chemistry. So in summary, we have talked about different types of non-aqueous titrations. We talked about the role of solvents in acid base reactions by considering the Bronsted-Lowry theory. We have also understood the three groups of non-aqueous solvents, that is amphiprotic, aprotic, and basic non-aqueous solvents. The Hammett acidity function we have also studied. Then we also studied the applications of non-aqueous titrants in analytical chemistry. So here these are some of the important questions that follow this chapter, and some questions along with answers have been given here. So kindly go through this and practice. So we will just take a break of 5 minutes, and then we will again continue with the next chapter. So now we will start with the next unit, that is redox titrations. So here in redox titration, we'll talk about the importance of redox titrations, redox potential, the electrochemical cells, redox titration curves, indicators, the titrations in non-aqueous solvents, and the applications of such redox titrations. So before beginning this chapter, we should understand what is redox reactions and redox potentials. Now let us consider this simple equation, that is Fe2 plus giving rise to ferrous plus 1 electron. So here in this case, the ferrous ions, they are getting oxidized to ferric ions, because the ferrous ions, they are losing 1 electron and they are getting oxidized to Fe3 plus. Now reduction is, on the other hand, reduction means the gain of one or more electrons. So here in the equation shown below, that is Cl2 plus 2e giving rise to 2Cl minus, we can say this is then the chlorine, it gets reduced to chloride ions, and the number of electrons involved in this process is 2. So looking at these equations, we can say that oxidation and reductions, they are always found together in a reaction. So that is, electron loss of one substance is always accompanied by the electron gain in another part. So consequently, what happens is there are no free electrons in a total chemical system. So such type of reactions where both oxidation and reduction are present simultaneously, they are called as redox reactions, and also sometimes called as electron transfer reactions. So let us look into this example that is given here. Cerium 4 plus ferrous ion becomes cerium 3 plus ferric ions. So here the electrons that is lost by Fe2 plus, they are picked up by Ce4 plus. Here in the end, when we look here, there is no free electron present in the system. So one system, it loses an electron, and other system, it takes up that electron. So this is the oxidation reduction reaction. We can also see it is accompanied by an increase in the oxidation number of a given species and a complementary decrease in the oxidation number of another species. So this is what here in this equation, the oxidation number of Fe, it increases from 2 to 3. Here it was 2 plus, whereas on the product side it is 3 plus. But the oxidation number of cerium, it decreases from Ce4 plus to Ce3 plus. So here it is what we call electron transfer reaction, and we can also see there is an accompaniment in the change in the oxidation number of both the species. Now coming to redox reactions as two halves reaction. So as a redox reaction, it involves both oxidation and reduction parts. So we can divide it into the total reaction, we can divide it into two half reactions. So here we can, the reaction has been shown here. Here Fe2 plus becomes Fe3 plus electron, which is an oxidation reaction. Cerium 4 plus takes up an electron and forming cerium 3 plus. So here this is a reduction reaction. So this first reaction concerning Fe2 plus is the oxidation of iron 2, whereas the second reaction that concerning the reduction of cerium 4, it shows the reduction reaction. So when we add up both these reactions, the electrons cancel out and we get the overall chemical reaction. The species which possess strong affinity for electrons, it cause the oxidation of other substances by abstracting electron from them, and they are called as oxidizing agent. So in this process, oxidizing agents, they themselves get reduced. Like here in this example, cerium 4, it acts as an oxidizing agent, but they are converted, reduced to the cerium 3 ion. Now whereas the species or the ions that readily give up the electrons, they cause the reduction, they are called as the reducing agents, and in the process of reduction, the reducing agent, it gets itself oxidized. These are some of the common basic fundamentals that we need to remember in a redox reaction. Then coming to redox potential. So if a system, it contains both oxidizing agent and its reduction product, there will be equilibrium between them and the electrons. Suppose if an inert electrode such as platinum, it is placed in such type of a redox system, like what in this reaction Fe3 plus and Fe2 plus, it will assume a definite potential which indicates the position of the equilibrium. Now if it acts as an oxidizing agent, then it will take electrons from the platinum electrode, leaving it positively charged. Whereas if the system has reducing properties, it will acquire a negative charge. So the magnitude and sign of the potential of the electrode system will be a measure of the oxidizing and the reducing properties of the overall system. Now there are different oxidizing and reducing agent which differ from one another in their strength. So an oxidizing agent, it can behave as a reducing agent in the presence of a stronger oxidizing agent. So for a reaction of the above type, when here of this type, it is shown here, where we have a pair of oxidizing reducing agents such that either of the species, they can act as an oxidizing agent or a reducing agent, then the direction is determined by comparing the redox potential of the oxidizing or reducing agent. So let us understand what is the significance of redox potential. Now in order to compare the strengths of different oxidizing agents, it is always necessary, that is to measure the potential between the platinum and the solution with that of a standard. So the standard here is always the standard hydrogen electrode, that we call it as SHE, or the normal hydrogen electrode, whose potential is taken as zero at all temperatures. Now, the standard experimental conditions for redox systems are those in which the ratio of the activity of the oxidant to that of the reductant is 1. So, for the following electrode, Fe3 plus to Fe2 plus, the standard redox cell reaction would be given in this form. So, the potential that is measured in this way, it is called as the standard redox potential or standard reduction potential. Here, some of the standard reduction potentials, that is E0, it is at 298 K. Here it is given here in table 10.1. Now, when we look into table 10.1, we see that the E0 is positive in some cases here, and then here, like up to here, we can see then it becomes 0. For 2 in this case, it becomes 0, and beyond hydrogen it is all negative in nature here, as we can see. Now a negative E0, it means that the redox couple is a stronger reducing agent than the hydrogen couple, whereas the positive means that the redox couple, it is a weaker reducing agent than the standard hydrogen couple. So these redox reactions, they enable us to predict. So looking at these E0 value, they enable us to identify or to classify which ion will oxidize or reduce other ions at particular molar concentration. So the most powerful oxidizing agents are placed at the upper end. These are the most powerful oxidizing agents which are placed at the upper part of the table 2.1, and the most powerful reducing agents here, they are present at the lower part of table 10.1. For example, let us say the standard reduction potential for Ce4 minus for this reaction is highly positive. That is, here the reduction of cerium 4 ions is so spontaneous that Ce4 minus acts as a strong oxidizing agent. Now, on the other hand, the standard E0 for the Zn2 plus ion is negative. So here it means that the reduction of Zn2 plus ions, zinc ions, is not favorable and it is a weak oxidizing agent, whereas metallic zinc is a strong reducing agent. So that is how we can classify, looking into the sign, to classify which type, which are strong reducing agents or which are strong oxidizing agents. Now here it is important that for many oxidants, the pH of the medium is very important, since they are generally used in acidic media. For example, in measuring the standard redox potential of MnO4 minus, Mn2 plus system, here in this case, it is necessary to state that the hydrogen activity is 1. But here, if we change the pH of this medium, then the activity of MnO4 minus, it becomes different. So here, the role of the pH is also quite crucial. Then coming to electrochemical cells. So what happens is the direct transfer of an electron from the donor to the acceptor, it has been best exemplified when we consider by immersing a piece of zinc in copper sulfate solution. It has been observed that copper is deposited at the surface of the metal. Then the copper ions, they migrate back to the zinc electrode and get reduced by thereby extracting electrons to it. So here this has been shown. This entire process has been shown in figure 10.1, which is called as the simple electrochemical cell or a Daniell cell. So here in this setup, we can see here zinc sulfate is taken and copper sulfate is taken. So the direct contact between metallic zinc and Cu2 plus is prevented with the help of a salt bridge, and that is mostly a saturated KCl solution or KNO3 or KCl solution. So the electrons here, they are transferred by means of an external circuit, and within the cell the current is carried by the ions. So here the electron transfer continues and the overall reaction for the Daniell cell is given here. Now when this stage is reached, there will be no flow of electrons. So here it is important that the overall reaction and position of the equilibrium remains same regardless in which manner the reaction is carried out. So here an electrochemical cell, it produces electrical energy because of the transfer of the reacting species and their condition to achieve the equilibrium among themselves. So here the cell is called as a galvanic cell and it is used to produce electrical energy. So for such type of cells, the measurement of EMF or the potential, it becomes very important. So for this process, the most commonly equation is the Nernst equation, which gives us the measurement of the EMF of the cell or the redox potential of each individual cell. Now let us consider for one electrode reaction where Mn plus, it gains n number of electrons to form the metal S, that is to form the M in solid state. Then according to Nernst equation, here the electrode potential can be given by this equation. This is called as the E is equal to E0 minus RT by NF ln of concentration of M upon concentration of Mn plus, where E0 represents the standard electrode potential, R is the gas constant, T is the absolute temperature, and N is the number of electrons that is participating in the reaction, and F is the Faraday's constant. So the logarithmic of this value can be used, and we can, the concentration here of a pure substance, that we know that of this, the concentration of M is always taken as 1, and of solids and liquids is taken to be 1. So this equation now becomes this form, and then we can write, after substituting the value of the R and the of the value of R and temperature at 298 K, and substituting the value of F, that is Faraday, we can find the ultimate Nernst equation. Here it can be given as from by this equation, minus E is equal to E0 minus 0.059 by N log of 1 Mn plus concentration. So for, let us write for some of Nernst equation for some common half cell reaction. If this is the half cell reaction, Cu2 plus plus 2E giving rise to Cu. So here for this equation, the Nernst equation can be written as E, the EMF of copper 2 plus to copper is equal to E0 minus 0.059 by 2. Here 2 is written because the number of electrons that are participating or involved in this half reaction is 2. So that is why in the Nernst equation, in the place of N, we can write it as 2. Similarly, for this equation, 2H plus plus 2E giving rise to H2, then we can write it as, the Nernst equation is given by this. So here P is given because it represents the partial pressure of hydrogen. Ordinarily, it is close to atmospheric pressure, but it is represented as P. So in the third case, if we look into this equation, so here the nonst equation here, in this case, the nonst equation is 6. We will look into this equation. The total overall equation represents 6 electrons. That is why we will represent the 6 electrons and we'll find out the value of this. So this is how we can calculate the EMF of any half cell reaction. Then coming to cell potential. So when two electrodes they combine to give a cell, the potential of the cell, it depends on the concentrations of the species, and then we can also develop a nonst equation for the same. So this has been done for the Daniell cell. So for reaction at the cathode for a Daniell cell, the reaction at the cathode is given by this equation. The reaction at the anode is given by this equation. So the overall cell potential can be calculated by the reaction at the cathode minus the reaction of the anode, and then here this is the cell potential has been found to be this. Now we can put a generalized, using this equation we can find a generalized formula for nonst equation, that is here E is equal to E naught minus 0.059 n by log of this is the concentration factor that we can use. Now let us here an example is given on how can we calculate the standard electrode potential of a cell which follow the following reaction, and it has been asked to calculate the standard electrode potential. So first in this case we will break the overall reaction, that is nickel, it gives rise to Ni2 plus 2 electron, 2 Ag2 plus, it takes up this 2 electron to form the 2 Ag. So here the total overall cell Nernst equation and the overall cell potential after substituting the values will be this. Then coming to redox equilibrium constant. The equilibrium constant of a redox reaction, it can be obtained by the application of Nernst equation. So here let us consider two redox systems that involve the same number of electrons. Here oxidizing agent oxidation 1 plus Ne, it gives to the reduced product R1. Here the R2 takes up oxidant 2 plus N, and this is the final overall reaction. So the equilibrium constant K, here it can be given by this formula. For the above two systems, the Nernst equation E1, E2 can be written like this. Now we know at equilibrium, here E1 is equal to E2. So rearranging the value and substituting all the values, we can find out that log K is equal to N1 by N2, E1 standard E1 0 minus E2 0 by 0.059. So this is the direct formula that we have obtained, and we can predict the equilibrium constant from, that is the log K, for any reaction using this equation. Like here it is shown in example 10.2. To calculate the equilibrium constant from this reaction, the value is given, we just need to substitute and then we can find the value for this. So then coming to redox titration curves. Now we know normal titration curves. Here we will talk about redox titration curves. So in redox titrations, the concentration of the substances, they that in the reaction it continuously keep changing during the course of the titration. So redox potential must also change during the reaction. By plotting the redox potential corresponding to different points in the titration, a titration curve that is similar to the curve that is obtained in an acid base method is obtained. So here this can be illustrated by computing the titration curve for a titration of 100 ml of 0.1 molar iron with zero point 0.1 molar cerium in the presence of dilute sulfuric acid. So here Fe3 plus cerium 4 plus giving rise to Fe3 plus Ce3 plus. So this titration, it involves Fe3 plus to Fe2 plus and Ce4 plus to Ce3 plus. Now we will call this 1 and 2. So here the Nernst equation, it can be written as E1 followed by, here one equation is involved, we can write Here, this is the non-stick equation in terms of Fe, and this is the non-stick equation in term of this. Then we can again, since we will substitute the value of the E10 that is given here, and we can find out this is the correct expression for E1 and this is the expression for E2. Now we know the equilibrium constant for both the reaction in terms of log K, it can be given in this formula. So log K, also putting all the values together, we can find the value K to be 7 into 10 to the power 11. So we can see as the value of K is very high in the order of 10 to the power 11. So we can say that this process or this reaction goes to almost completion. So this is how we can find out the redox titration curve potential, sorry, redox titration potential. Then let us understand the potential before the before the beginning of the titration. So in the beginning the solution contains only Fe2 plus and may have very less amount of Fe3 plus because of aerial oxidation. Now here, because the concentration of Fe3 plus is very small, the calculation cannot be done or it has relatively no significance. Then what happens? The potential after addition of 10 ml of zero point 0.1 molar mercury. So we have Fe2 plus in iron solution and then we add 10 ml of zero point 0.1 molar Ce4 plus. So here the concentration of Fe2 plus and Fe3 plus here would be in the ratio of 90:10. So then we will compute the value. So here Fe2 plus by Fe3 plus becomes this. Then the value of E becomes this. Then after the potential after addition of 50 ml of zero point 0.1 molar cerium 4 plus. So here the concentration can be given as this. Then after addition of 90 ml of zero point 0.1 molar Ce4 plus, then the initial concentration of Fe2 plus becomes 10 and the final and the Fe3 plus it becomes 90. So this potential after adding this we just need to put the value of all the values and then we can compute the E1 and E2. This is how. So at the end of the finally after adding 100 ml of zero point 0.1 molar cerium Ce4 plus into Fe2 plus solution, we find out that Fe2 plus is equal to Fe3 plus and C3 plus is equal to Ce4 plus. This is the equivalence point and this is the potential of the equivalence point. So therefore at this stage there won't be any Fe2 plus and with further addition of reagent only the ratio of cerium will change. Nothing will happen to the concentration of Fe2 plus or at the Fe3 plus, but only the ratio of C3 plus to 4 plus will change. So here again potential after addition of 100.1 ml of this is the of cerium, this is called as the post equivalence point potential because the equivalence point has already been reached but still we are adding 100.1 ml of 0.1 ml extra of Ce4 plus solution. So as a result here the Ce3 plus the curve becomes this, the ratio is 100 to 0.1. Then after addition of 101 it becomes 100 by 1, 110 it becomes the ratio becomes 100 by 10. The addition of 190 ml it causes 100 by 90. So this is the potential after addition of 190 ml of zero point 0.1 molar cerium into the solution. So here the whole titration it can be plotted, the whole titration it can be plotted in this way from figure 10.2. It shows the titration curve of 100 ml of 0.1 molar iron with 0.1 molar cerium. So here to begin with, here Fe2 plus excess is present. This is the equivalent point. Even if we keep on adding Ce4 plus, the Fe2 plus ratio will not change. Only we see an increase in the potential of the that is relative to the Ce4 plus ion. So this is how we calculate the equivalence point in terms of redox potential. Now this we can see The general appearance of this curve is similar to that of any acid-base titration. So this looks similar to the titration curves that is either obtained by titrimetry or pH titrimetry or conductimetry. So it can be noted that the potential which changes slowly in the early stages, it changes very abruptly. After the equivalence point is reached, the change is very prominent. The magnitude of potential change, it evidently depends on the difference between the standard potentials of the two reactions that are involved. That this curve, it is symmetric about the equivalence points when the oxidants and the reductants, they react in equimolar amounts or exchange same number of electrons. However, we can see it would not be symmetric about the equivalence points when they have different number of electrons. Here, beyond this equivalence point, it is the curve is symmetrical in nature. However, before the equivalent point is reached, the curve is not symmetrical in nature. So redox titrations, they are usually independent of dilution, because Nernst reduction equation, it considers the ratio of the concentrations, and it does not, with the concentration does not alter with dilution. So here it is worth mentioning that the break in the potential in the titration curve can be used in the selection of an indicator. So that is how titration curves are important. Now coming to redox indicators. So a redox indicator is a compound which can undergo a redox change, and the color is changed depending upon the potential of the solution. That is, the oxidized and the reduced form of the indicator, it has different colors. So here this is the general equation, indicator reaction, that is represented. So if we look into the Nernst equation, we can write it in terms of concentration. This can be written. So alternatively, as the color, we know that color is proportional to the concentration of the species. That is, this according to Beer-Lombard's law, the color or the absorbance is directly proportional to the intensity. So we can write it like in this form that is given in yellow. That is, the redox indicator will show color X if the intensity of this color is at least 10 times greater than the intensity of Y. So here, in other words, we can see color X will be seen when the solution potential is this much, and color Y will be seen when the solution potential is this much. So an intermediate potential values of the solution, the indicator will show a mixture of both the colors. When the equivalence point has not been reached, or they are in the intermediate form, both the colors of X and Y will be seen. So from these expressions, we can conclude that a redox indicator involving one electron in the Hubsan reactions, they require a potential change of this to this. So the potential range of the color change for an indicator can be calculated theoretically by this equation. So now let us take an example of titration of iron with cerium in acidic medium. So in this titration, 110 phenanthrolene iron, it is used as an indicator, that is ferroin. So it is then the three molecules of ferroin, they are coordinated to iron to form a red octahedral indicator complex, this, which is indicated by this. Then the color change of the indicator is due to the oxidation of Fe2 to Fe3 in the indicator. The reduced form, that is Fe2, it has an intense red color, whereas the oxidized, that is the Fe3, it is pale blue in color. So the indicator half reaction is this here. So due to the change in color, we can calculate the Hubsan reaction. Here, another example has been shown taking the case of diphenylamine, which is one of the earliest redox indicators. It was introduced by Knoop for the titration of iron Fe2 plus with potassium dichromate. The reduced form of this indicator is colorless, and the oxidized form, it has a deep violet color. So this is the reaction. This is diphenylamine, that is DPA. Here it is colorless in the reduced form, but when oxidized form, it occurs as a diphenylbenzidine it occurs as a deep violet. So the first reaction, it involves the formation of the colorless diphenyl benzidine. It is irreversible. The second, however, gives a violet color and is reversible in nature. However, this indicator, it suffers from the drawback that its solution must be prepared in concentrated sulfuric acid. So the sulfonic acid derivatives, they are frequently used instead. So the barium or sodium salt of this acid, they are soluble in water and may be used to prepare aqueous indicator solutions. So here in table 10.2, we can see some standard reduction potential values and the colors of the oxidized and reduced form of some indicators. Suppose we talk about methylene blue. The color of the reduced form is colorless. The color of the oxidized form is blue and the standard transition potential is 0.53. Similarly, for areoglucin A, the reduced form is yellow-green in color, whereas the oxidized form is blue-red in color, and the E0 is 1. So this is how redox indicators work. Now we'll talk about redox titration in non-aqueous solvents. The discussion that we have so far, we were talking about redox potential in aqueous medium. Now we will talk about the redox titrations in non-aqueous solvent. Now there are various which have we have a different compounds for which non-aqueous solvents are liquid, like the compounds that are insoluble in water, the compounds which react with water through hydrolysis or oxidation, or the compounds which are decomposed by aqueous reactions. So for such type of compounds, there is a need for non-aqueous solvents. Then what should be the criteria for the solvent selection? The following are the properties: that the solvent should be resistant to the attack by the reagent. So this permits the reactions to be carried out over a wide range of potentials. So for example, dimethyl formamide, that is DMF, it can be used as a solvent for redox titrations involving chromium, but it is oxidized even by mild oxidizing agent. So that is, on the other hand, nitrobenzene is resistant to oxidant, but it is susceptible to reduction. So acid, it may so this makes it a good choice as a solvent for redox determination in aqueous media. The solvent should be capable of keeping reactants and products well in solution. The third point is, in order to evaporate these conditions, the solvent may be very easy to handle. Like some solvent, they have very favorable dielectric constants, but they are difficult to purify. Then some solvents, they absorb water from the moisture and thus they need to be protected from air. So many solvents like ammonia, sulfur dioxide, they have low boiling points and require low temperature conditions. So some solvents are toxic and thus the use is not permitted in analytical chemistry. Thus, choice of solvent becomes critical. Then coming to some of the characteristics of common non-aqueous solvents. So some of the commonly used solvents for redox determination are acetic acid, because it has a low dielectric constant, it is difficult to purify, and it is not even convenient to handle. Thus, it fails to meet the criteria, yet it has been much widely used because of its availability at low cost for acid base titration. The most common oxidation reduction titrant that is used is lead acetate. Perchloric acid and sodium acetate have been much widely used in analytical chemistry. Then coming to acetonitrile, it is a versatile solvent, and the reasons for its popularity is that it is a convenient liquid, it is readily available, it has a wide electrochemical range, it has a moderate dielectric constant and low toxicity. However, the disadvantage of using it is lies in its purification, and it has a tendency to polymerize in presence of acids and bases. But the acetonitride is still a good choice. Then coming to DMF. DMF is a solvent for which only few applications has been reported. It has a dielectric constant close to that of acetonitrile, nitromethyl, and dimethylastamide. It dissolves many organic and inorganic compounds. It has a wide electric liquid range, and it is thermally stable. Also, it is readily available and it has low toxicity upon inhalation or contact with skin. Purification of dimethyl formamide is quite okay and is not much tedious. Then dimethyl sulfoxide. DMSO has received considerable attention because it as an electrochemical solvent, because it has acts as a mild oxidant in conjugation with other reagents. It is also a good solvent for many organic compounds, and it has a potential range of over 4 volts. DMSO is not very toxic, but it also it has it can be used quite easily. So many other solvents like acetone, tetrahydrofuran dioxane, they have been used in non-aqueous titrimetry, but they are quite limited. Now coming to applications of redox titrations. So there are some common oxidimetric and reductimetric applications. So here we'll first start with oxidimetric reagents. Potassium permanganate, KMnO4. It is a versatile reagent, oxidizing agent in acidic, neutral, and alkaline medium. In acidic medium, KMnO4 is a strong oxidizing agent because here MnO4 gets reduced to Mn2 plus with the help of 5 electrons, and the E0 is 1.51 volt. In neutral medium, KMnO4 is reduced to manganese dioxide. 3 electrons are involved, and oxidizing agent, it is the E0 is 1.68 volt. So on the other hand, in strongly alkaline medium, the oxidizing property, it is attributed to its reduction to manganate ion, that is MnO4 ion is converted to MnO4 2 minus. So here KMnO4 is, we can see, it is a strong oxidizing, very much versatile oxidizing agent. So in typical determination of reducing agents using KMnO4, we prepare a standard solution of KMnO4. Then the standard solution of KMnO4, it is standardized against sodium oxalate. That is the primary standard. KMnO4 not being a primary standard is a big disadvantage. Okay. So the standardization of KMnO4 can also be done by sodium oxalate or oxalic acid, that is given by this equation. So the oxidation of oxalate with permanganate ion at room temperature is slow, and it requires the following. Here the following equations have been shown how oxidizing it is done, the property, oxidation property of KMnO4. Then coming to cerium 4 salts. Cerium 4 is a strong oxidizing agent in acidic medium. Here, the E0 values are 1.7 volt in HClO4, 1.6 in NaHNO3, and 1.4 in H2SO4. Here, it can be stored almost indefinitely and may be employed in the determination of reducing agents. But it used as the use of cerium 4 salts as a self indicator is not, it is not used, and it is preferable to use ferroin with, to understand ferroin for such purposes. Then potassium dichromate. Potassium dichromate is a strong oxidant. The reduction equation here, this is the equation. The E0 is 1.33 volt. It is a primary standard, and it is obtainable in a high state of purity. The endpoint in titrations with dichromate ion is generally detected by using suitable redox indicators. Although potassium dichromate is a weaker oxidizing agent than KMnO4, it can be used in acidic medium to determine most compounds that can be titrated with KMnO4. So the determination of Fe2 is the most important application of potassium dichromate. Then potassium bromate, it is also a strong oxidant in acidic medium. It is a primary standard, and the reagent can be obtained in a pure state. Its standard solution can be prepared by direct weighing. So here, then the endpoint is indicated by the formation of yellowish color, due to which bromine is released. There are many compounds which do not react with bromate as such, but bromine liberated from these reactions and is an, here it is used. Bromine is quantitatively used for saturating the double bond in such type of reactions. Here bromine saturates the double bond, that is here, that is present here. The above reactions, they are used for the determination of unsaturated organic compounds. Then potassium iodate, this compound, it is quite available in a pure state. The reaction of iodate with iodide, it is analogous to bromate bromide reaction. Here it is shown here, and it is useful for the generation of known amount of iodine. Then iodine, the I2 to I minus couple is of medium oxidizing power, whereas iodine is a weak oxidant. Iodide is a relatively weak reductant, Hence, this couple, it can be used for the reduction of both determination of both reductant as well as oxidant here. The I2 I minus couple, 2I minus couple. So if the couple to be determined has a standard potential lower than that of 0.54, then this reaction would proceed to the right. So iodine, we know it is sparingly soluble in water, and its aqueous solution is prepared by adding potassium iodide. So in such solution, iodine is in the form of a triiodide, but it is usually expressed as I2 in these reactions. The iodine solutions are standardized by means of arsenous oxide. Here, that is a primary standard, or sodium thiosulfate. Starch is used as an indicator in all iodine reactions, and the endpoint is indicated by the formation of a blue color. The method in which iodine is used for the determination of reactants is called as iodimetry, and the method in which iodide is used for the determination of oxidants is called as iodometry. Then coming to reductimetry reagents. The standard solutions of the reducing agents, they are not as widely used as oxidizing agents because most of them are oxidized. These reductimetry reagents, they are easily susceptible to oxidation by the oxygen present in the atmosphere. They are therefore less convenient, and uh, they are used very less. Thiosulfate is the only common reducing agent that is stable to aerial oxidation. However, some other stronger reducing agents than iodine are sometimes required, like iron. It is a weak reductant. It is slowly oxidized by air in sulfuric acid and finds common use. Then chromium and titanium, these two are very powerful reducing agents, but they are readily oxidized by air and consequently are difficult to handle. So the reaction equations here, they have been shown. Chromium and chromium has been used for the titration of oxidized forms of copper, iron, silver, gold, bismuth, etc. Here, so in summary, here we can talk about the various types of oxidation reduction reactions in volumetric analysis. The use of such reactions we have discussed today, the redox indicators, the redox titrations, the scope of these reactions. We can talked about various types of reductimetric and oximetric reagents. So here some of the questions that have been given here with the possible self-assessment answers that have been given. So with this, we finish unit 10 today. The redox reactions we have completed today, redox titrations in. So this much for today. We will continue the subsequent units in the next class. Thank you for today.